this lecture we will discuss 2 to the power k factorial design, 2 to the power k factorial design. Actually, we are saying that factorial design with 2 levels or 2 level factorial design also, sometimes we say like this. Okay. What does it mean? Suppose there are k number of factors, each with 2 labels. Suppose if I consider the k equal to 2, then our number of factors is 2 and a and b, and now instead of a having a labels, b having b labels, we are saying the small a equal to 2 and small b equal to 2. So, as a result, a having 2 labels as well as b also having 2 labels. Then the design will be 2 to the power k equal to 2 to the power 2 design. So, as such if there are k labels, kth factor, then the design will be 2 to the power k. This is what we will be introducing in this lecture, and later we will continue few lectures on 2 to the power k design. So, in today we will discuss that why this kind of design is needed, and then what could be the statistical analysis and how the parameters will be estimated. So, you just consider a case with full factorial design. Suppose I have k number of factors and each having different levels, a having a number of labels, b having b number of labels, c having c number of labels, like this. If my number of factors is 10, or let us number of factors is 3 only, and then the number of independent runs will be a, b, c, and if I have n replication, this is what is the total number of experiments to be conducted. Suppose if I say a equal to 5, b equal to 5, c equal to 5 and n equal to 5. So, that means my a, b, c, n, this will be 25 into 25. So, this will be 625, I think. So, that number of experimental run will be very large. Okay. So, number of experimental runs will be very large, and every experimental run cost. For example, it requires raw material, it requires operator, it requires time, it requires process to be used. So, it may be infeasible if we require this much of experiments to be conducted. Maybe the process owner will not allow us to do this. Under such situation, can we do some kind of adjustment where that instead of going for a label for factor a with a different levels, rather make it 2 labels. So, in that case what will happen, a, b, c, n, when each of the factor at 2 label, that means 2 to the power 3 into n. So, you require 8 n total number of runs for 3 factors. Now, if I consider n equal to 5, then you require 40 experimental runs to be completed. So, possible, it is easy, it will be less costly, but if you want to use these kind of things, you have certain assumptions that is to be satisfied, and definitely the purpose that will be served by analyzing this experimental data will not be the exhaustive one, because it has reduced levels. So, it will be used for specific purposes. So, what are the assumptions? The factors are fixed, the designs are completely randomized, the usual normality assumptions are satisfied. As each factor has two labels, response surface can be approximately linear. If it is not, then what will happen? In between the nonlinearity, you will not be able to estimate. For example, you think of a design where two labels, so low and high. So, this is low and this is high, this may be low and high. Then this is A and B. Now, what will happen? Suppose this A and B, if I want to go for the response surface, so you may be getting a surface something like this, or approximately linear, but if the surface having some kind of, suppose nonlinearity at this point, some kind of quadratic part. So, you cannot capture this because your experimental data are coming from these 4 factorial points. So, if it is assumed that, or it is quite practical that okay, this surface is linear, a parallel or approximately parallel, then this kind of 2 to the power k design will help you. So, as a result also the purpose is limited. I told you these designs are widely used in factor screening experiments. Factor screening experiment mean, suppose if there are k number of factors, how many factors are significantly contributing on the response and how many are not. So, your whole purpose is to eliminate those insignificant factors and to reduce the number of factors from higher level, from a high level to a lower level, and you can do further experimental run with small factors, maybe completely full factorial design you will employ there. So, let us now understand that the effect parameters calculations with reference to a 2 to the power 2 factorial design, which is the most simple case of 2 to the power k factorial design. Okay. So, we will do this kind of tabulation. There are two factors A and B. Now, each has two labels minus and plus. So, we are denoting like this: A minus plus minus plus, low high B. When A low, B low, A high, B low. So, that means low low high high, and the combination is A low, B low, A high, B high, A low, B high, B high, A high, B high. So, these are the points: low low, high low, low high, high high. And suppose in each these experimental settings you have done 3 experimental replication is 3 experimental runs conducted. Obviously, these are random experiment, randomized one. So, then suppose the response values is 4 here, 7 here, 3 here, and here 12, 9, 7, like this the data you got. Okay. So, what happened here then? Then you have 3 runs in each treatment settings. So, we want to first know the what is the total here. This total will be 4 plus 7 plus 3, 14 here when low low. Similarly, at this point is 28, similarly at this setting is 38, similarly at this setting is 36. These are known as totals. These totals are given a special notation in 2 to the power k factorial design. The reason is it helps us defining many things, also in computing the effect as well as the sum squares. What is the notation? The notation will be 1 when both are at low level, that is minus minus. Then we are saying A, if A changes to plus, when A goes to high, factor A goes to high, factor A at low level. We are denoting B, the situation when A at low, B at high, and we are denoting by AB when both at are high. But this is the notation from, that means this is my 1, this is A, this is A, this is B, and this is AB. So, I can say these are the experimental combinations. But in addition, from total point of view, we give some number to all those things. These are nothing but the total values of y response at 1, at this point, at this point, at this point, at this point also. So, this is the situation, but we also give that what is the total here. So, what is the total here? What is the total here and here? So, with reference to this example, then this will be 14, and A will be 28, B will be 38, and AB will be 36. So, what I mean to say here, that you have seen the situation like this. Situation is that when A low, B low, A, B, and suppose experimental runs, low low, this setting is denoted by 1, then high low A, that means low high B, and high high AB. And we have calculated total here with reference to this 1 is representing 14, 2 is representing total value, that is A is 28, B total value is 38, AB total value is 36. So, this will be the experimental setting one hand. Another hand, the number means, suppose if there is one replications only, then this value is the one y value. So, sum of y values, sum of y values. Okay. So, then we want to estimate the effects. What are those effects? What is the A effect? Suppose what is the B effect, and what is the interaction effect? AB interaction effect. So, A is changing from minus to plus or minus 1 to plus 1. You can write minus to plus or minus 1 to plus 1. B from minus 1 to plus 1. So, that means now A effect will be the mean values, here total you get here, the mean values of y when A it has high level minus mean values of y when A it has low levels, irrespective of level of B. So, that is the main effect of A equal to y, A at positive, that is y bar, A at positive minus A at negative. That means, when A at high value high, what is the average of y? When A at low, what is the average of this? Similarly, main effect of B will be same thing, y bar B high minus y bar B low, this plus minus for high and low. Here irrespective of B, and here irrespective of A. Then, and what will be the interaction effect AB? That will be when, that means the y bar AB same level minus y bar a b different level. What does it mean? That means either the same level means a at positive or negative negative. Here either positive negative or negative positive, means a at high or low, that is the same level, and a at high, b at high, a at low, b at low, that is same level. Here what is happening, a high b low or b a low b high, that is the different level. So, what is the average of this, and then minus the average of this. So, now what will be the average of this, the y total at these 2 points. So, this if there are n replicates, here also n replicates, then 2 here n plus n 2n will be the observations. So, 1 by 2n and the total. So, that means where 2n will come out. What you will get? You will get a equation like this. Why? The equation will be something like this. Suppose I want to know what is y a positive bar. So, we know the total here is 1 within bracket, here is a, here is b, and here is a b. So, y a bar is when a at high, what is the total then? A b plus a. What is the number of observation? Here n, 2n. Then minus, this is similarly y a minus bar, this will be this and this, average b plus 1 by 2n. Then ME, that effect A will be the difference between these two, y a plus bar minus y a minus bar, then this will be a b plus a by 2n minus b plus 1 by 2n, then the resultant is 1 by 2n a b plus a minus b minus 1. So, see this situation, this is interesting one. When we are talking about A effect, you see that the small a is coming wherever small a is there, that those are basically summed up, and wherever there is no a related terms are there, they are subtracted. So, using this, if I want to tell you what is the effect of B, so B effect is y b plus bar minus y b minus bar. So, this will be basically when b plus a b plus b divided by 2n, when b minus a plus 1 divided by 2n. So, that means a b plus b by 2n minus b plus 1 by 2n, then this will be 1 by 2n into a b plus b minus a minus 1. Interestingly, you are getting the same one, that we are interested in b, the small b is related to b. So, here b term is there, b term is there, this is plus, wherever there is no b term, this is minus. Okay. Now, what will be the a b effect? A b effect is when both are at same level. So, that means either high or low, and both are at different level. So, y bar a b same minus y bar a b different, that is what I said. So, same means a b plus 1 divided by 2n minus a plus b by 2n. So, this will be 1 by 2n a b plus 1 minus a minus b. Okay. So, here when if we see that a is 1 by 2n a b plus a minus b minus 1 B if you see, that is 1 by 2n, AB plus B minus A minus 1, AB if you see, this is 1 by 2n, AB plus 1 minus A minus B. Okay. So, you have interestingly within third bracket a quantity, third bracket everywhere a quantity you have, this is known as contrast. Suppose we say this contrast C. What is saying here? That means when I keep in A effect, contrast is if I change from low to high, what is the change? So, that means with reference to low, what is the ith position? Similarly, for B and for AB, that means same level to different level. So, contrast, this value is giving us contrast value. Now, we have two part. One part is the what will be the division factor 2n, 4n, whatever may be, that you have to identify, and you have to know contrast. If you know contrast, you are in a position, contrast for A, contrast for B, contrast for AB. As such, if you have many more factors and their interaction, you have to know the contrast, then you will be able to find out their effects. Okay. So, with this description and given this data, we found out that A equal to 2. What does it mean? If you change A from low to high or minus to plus, then the y change will be 2 units. Then the main effect of B is 5.34. If you change B unit from minus 1 to plus 1, that means 2 units change in B in this coded scheme minus 1 to plus 1 will change y by 5.34 units, and the interaction effect is minus 2.64. So, that means if you change from the same level to the different levels, so there will be y change will be in the y will be decreasing by minus 2.67 units. So, this is from average point of view. Now, as I told you, the contrast point of view, if you see use the contrast, the same equation you will come and same formulation you will see. So, what we have discussed so far, then we have discussed that 2 to the power 2 design or 2 to the power 2 design is the special case of 2 to the power k design, and 2 to the power k design is the special case of full factorial design, that we have discussed. Then we have showed with reference to the power 2, I have told you that how to compute the effect parameters A, B and A B. We have seen another important thing called contrast, so which will be denoting by C. Okay. So, now you know how to compute this A, B and A B. Also, you will be I will tell you how to compute mu later on, that grand mean. And now, we will see that with reference to 2 to the power 2 design, how to compute the sum squares, how to compute the sum squares. Okay. So, if I go back to estimate of effect of A, and if I say this is the contrast, and then how this contrast is coming from the data. Suppose I say that we are denoting this A, B and A B. What we have seen that A at low, B at low. So, minus 1, minus 1. This we have denoted by 1. Then when it is plus 1, this is minus 1, we denoted it by A. When this is minus 1, this is plus 1, denoted by B. When this is plus 1, this also plus 1, denoted by AB. Okay. So, these are basically effects of on y, that values. Now, then if I want A B, you multiplied this row with this row. If you multiplied the 2 minus into minus, this will be plus 1, this will be minus 1 and this will be your minus 1 and this will be your plus 1. So, you are right here 1, here 1, here 1, 1, 1. So, this row represent contrast for A, this row represent contrast for B, this row represent contrast for CB, AB. This is what is contrast. Now, when we say this basically gives you this basically gives you this fine, basically that effect is there. So, if I go back again, let it be like this. So, I am saying this portion is the contrast while multiplied by this. So, by this is basically the constant basically constant for A, for B and for AB. Now, if when you multiply this with this, you will get this contrast. When you multiply this with the effect, you will get this contrast, and when you multiply this with this, you will be getting AB contrast. Okay. So, essentially what happened, that if I say this into this, then it is nothing but minus 1 plus A minus B plus AB, first one. And then if I see that what is the A effect, 1 by 2 n sum of AB plus A minus B minus 1, this is 1 is there. Okay. So, this way this is basically this is coming. So, this is the contrast. So, we can say that this is the C's. So, general C for small c for A is like this, in this case minus 1 plus 1 minus 1 plus 1, this is for A. For B something like this. Now, this is what is represented here. Now, how do you that mean then the contrast of A is, as I told you, this row multiplied by the effect row. A's row multiplied by the contrast constant for A and effect values, these two multiply, you will get contrast A. If this and this multiplied, you will get contrast B. If this and this multiplied, you will get contrast C. Now, how to compute the sum square contrast? So, the sum square contrast, if I say what is the sum, SSC means sum square contrast, sum of squares contrast, sum of square contrast. So, this will be sum of I equal to 1 2. Now, you have to see that if it is A, you have to know where from changing this one. Suppose I am writing 1 to A, then this is C I and Y I dot bar, the total square divided by 1 by n sum of C I square, I equal to 1 to A, and ultimately this will give you this quantity, this will give you, if I change it to I equal to 1 to A and C I, then Y bar to Y I dot, because this is the total, and if I make this square, then the n square will come out, then n sum total of C I square I equal to 1 to A. So, so here again I have used the word A I equal to 1 to A. Rather, let me tell you, basically we are saying that these are the effects against each treatment combination. So, let me write out, not write out A, maybe I can write out the treatment combination. So, let this is my, this is P. If there are such treatment combinations are there, no problem, whatever may be, you understand that how many treatment combinations are there, the -1 + 1 -1 + 1 for each level, you will be able to do it. This is P, this is P. So, now if I want to know the contrast for SSA, suppose I want to do this SSA, then what I will write down, what is CA for me? The CI's values are -1 + 1 -1 + 1. So, I have to multiply this by the total. Total is here, when it is -1 it is 1, this is A, this is B, this is AB. So, that means if I multiply by CI and YI total, so if I multiply these two columns, so these two columns, what it is giving me? It is giving me -1 plus, or I write like this, plus A minus B plus AB, which is nothing but AB plus A minus B minus 1. So, that means this is my contrast square. So, I can say this is contrast, if contrast is C, then C square, or other way I can write contrast square. What is the lower value then? Lower value is basically you are squaring Ci square. So, Ci means this multiplied by this will give you only all 1, -1 square root, this all 1. So, sum of this will give you I equal to 1 to A Ci square will be ultimately what? This will be this many. Suppose if I say P here, so it will be P. So, now in this case, what is the settings? 4 settings. So, sum of 4. So, this will be 4. So, then this quantity is 4 into n. So, please remember this one, interesting one. So, when you want to compute any effect, you first know what is the effect, either A, B or AB. As such, for others later on we will discuss. Find out the contrast. So, contrast is CA, CB, CAB. If you want effect, so effect of A, then it is contrast divided by 2n divided by 2n divided by 2n. These are the effect, equal to this, equal to this, equal to this. If you want SS, then what will happen? For A, the SS will be contrast square by 4n, means I can write contrast square by 2 to the power 2n, here 2n 2 to the power 2n. This is CB square by 2 to the power 2 into n, and this will be CCAB square by 2 to the power 2n. So, your things become very simple, because this contrast is known for each of the effects. When then the resultant quantity here, what is happening? SSA is this, SSB this, and you just the SSA will be this quantity is 12 square by 4 3 12, it is 12 only. SSB is this, SSC is this, the AB is this, then SST will be the square of all the observation, then sum minus the correction factor, and like this. Okay. So, how do you compute the mean value then? In case of mean value, ultimately what is mean value? For all settings, whatever values are there, all total divided by number of observations. So, all total will be possible if it is 1, this is A, this is B, this is AB, That means you create a contrast kind of thing for all 1 only, and then multiplied by the effect, that is 1 A, B and A B, then you will be getting 1 plus A plus B plus A B. Obviously, there will be how many observations are there? Here n, here n, here n, here n, then 4 n observations will be there. Total observations. So, this will give you the estimate of y bar. Y, if it is double dot, I think I j k, k is there, this which is basically estimate of mu. Okay. So, now once you know A, B, all those things, squares are known, and you will know that whether that is significant or not, and accordingly you decide. Interestingly, here what will happen, whether A, B, all F it, this will be only 1 degrees of freedom. So, as a result, you require to see the error degrees of freedom, and as all the effect will be 1 degrees of freedom. So, F 1 and error degrees of freedom per GB, this value once you require to take for this, any value F value more than this value for this example will be significant. Okay. Now, I will show you very quickly that how regression approach, that means what we have seen earlier, that the we in regression A we denoted by x1, B we denoted by x2, and then A B basically it will be x1 times x2. Okay, so then your fixed effect model is y I j k equal to mu plus tau I plus beta j plus tau beta I j plus epsilon I j k. Our regression will be, we will write like this: y equal to beta 0 plus beta 1 x 1, beta 2 x 2 plus beta 1 2 x 1 x 2 plus epsilon. Okay. So, now what happened, we know the different settings, those different settings we will denoted by observations. So, settings are with reference to A means x 1, B means x 2 and A B means x 1 x 2, that setting. What will happen? First setting is A minus 1, this is plus 1, then this one is plus 1, this one is plus 1, this is again minus 1, this is minus 1, then this is plus 1, this is minus 1. So, then mean independent run 1, 2, 3, 4. Then what will be x 1, x 2? This will be minus 1, plus 1, plus 1, minus 1. Okay. So, this is our, and then what happened? You will get y total somewhere, y total, you will get y total. For this it is 1, this is A, this is B, this is A B, as if this is what is our data for regression. So, we have 4 independent settings, there are x values, there are y values also. In addition, what we require here, we require a constant called x 0, which will take always 1 for beta 0. This will be writing like this 1 1 1 1. This manner we will write. Okay. So, then your what you do, you find out SSE will be epsilon square. If I write this I, then this is I 1, this will be I 2, this will be I 1 and this will be I 2, and this is epsilon I. So, that means SSE will be I equal to 1 to n, here it is 4, fine, epsilon I square, this will be sum of I equal to 1 to n beta 0 plus beta 1 x I 1 plus beta 2 x I 2 plus beta 1 2 x I 1 x I 2, this y 0, this one y I minus this, yi minus this minus this minus this minus this square. So, what you do now, then del SSE by del beta 0 put to 0, del SSE by del beta 1 put to 0, and this manner you put and you solve all those things. The resultant equations is a simple one is like this. So, this is my function that is to be minimized, this is basically the SSE. If you make del L by del beta 0 is 0 and then put to 0 equal to 0, you will get this equation. If you do with beta 1, you will get second equation, beta 2 third equation, beta 1 2 fourth equation you will be getting. And here you see the sum of x I 1 will be 0 because x I 1 means sum of this column minus 1 plus 1 minus 1, this will be 0, this column will be 0, this column sum all sum column will be 0. And if you take the square, then it will be here are 4 independent things, it will be 4 square and sum, that will be 4. So, that is why what happened, you are getting this equal to I equal to 1 to this y I, this total will come here, this is the all sum, and here with reference to this as x I 1 will be multiplied. So, that the minus 1 plus minus plus is coming. Here the x 2 will be multiplied. So, that is why what happened, minus minus plus plus will be multiplied with this, and here what happened, that same and different level. So, same level plus plus minus minus. So, this total is coming. Now, putting the other constant, this equal to 0, this equal to 0, sum of this, what you will get, if you put these values as 0, then from this equation 4 beta 0 plus 0 plus 0 plus this also will become 0. So, that means 4 beta 0 is equal to this, then beta 0 equal to 1 plus AB by 4. Similarly, beta 1 4 beta 1 will be this, 4 beta 2 will be this, 4 beta 1 2 will be this, you will be getting this beta 1 beta 2 beta like this, these are the estimates. Okay. So, once you get these beta values, so you will see that the beta values are nothing but A by 2. Beta 1 is A by 2, beta 2 is B by 2, beta 1 2 will be AB by 2, the effect parameters what you have estimated in fixed effect model. Now, the advantage of having this model is that we can go for response surface. So, this is our the run, these are the data, and this is the response surface plot for this particular equation. Here x 1 x 2 and how y is changing, you see that it is almost a plane, perhaps because of this what is the beta 1 2 value is you have seen that beta 2 effect is significant earlier, but beta 1 beta, where is your beta 1? Beta 1 as well as this beta 1 2 is not significant will be there. Anyhow, those things you will be tested through that regression model, the way we have done, that can be same way it will be tested. Now, from here we are giving a contour plot, like for a different settings of x and x1 and x2, what will be the range of y values here. So, there a color combination, suppose if it is a maximization problem, what you want, y value should be maximum, that is greater than 13 year, when that is the zone, this is the zone of interest where you can set your process. Suppose if it is a minimization case, then with reference to this is the zone where y values are, you will be getting minimum y values. Okay, but if it is some target value is there, suppose 10 to 11, then this is the zone which gives you the y value 10 to within 10 to 11, and accordingly you choose what will be your x 1 and x 2 values. Okay. So, I hope that you have understood, and you please remember that there will be test of assumptions like normality, homoscedasticity every time. So, you have to do all those things. It is simple. Once you have the residual, you do residual analysis and get it done. Thank you very much. See you again.